Okay, today we're going to look a little bit more closely at entropy. And entropy is best defined when we talk about the universe. The entropy of the universe increases during every spontaneous change occurring anywhere in it. So every time a spontaneous change occurs, the entropy here, when it occurs here on Earth, the entropy of the universe increases. So the entropy of the universe is always increasing. Entropy, now remember, is disorder or randomness. Okay? That's the second law of thermodynamics. The entropy of the universe for any spontaneous change is going to be greater than zero. It's going to increase. Now, we can divide our universe, remember, into two parts, a system and its surroundings. So the entropy of the universe is the sum of the change in the entropy of the system plus the change in the entropy of the surroundings. One of them will be the opposite sign to the other because when heat comes out of the system, it goes into the surroundings. Now, the change in entropy for a constant temperature isothermal process is defined as the delta S of the universe is greater than or equal to the heat flow when the process is reversible divided by the absolute temperature. Now, what we mean by a reversible process is a process always has two forces, one pushing it forward, one pushing it backward. So if both of those two forces, if the process pushing it forward is greater than the one backward, then the process will occur as we expected in the forward direction. But if the force for the reverse were larger, it would go the opposite direction. Now, what we mean by reversible change is those two forces, the one pushing it forward and the one pushing it back, are equal. Now, obviously, if that were the case, no movement would take place. So what we have to do is imagine a process where the push forward and the push backward are equal, but we just occasionally, very, very slowly, lower the opposing force. And then the process occurs essentially over an infinite amount of time, which obviously we can't do. But it is that idealized process where the heat change in the universe would be exactly equal to Q divided by T. It's only for a reversible process. And like I said, we can approximate that, but never, ever duplicate a reversible process. It's just one that we imagine that allows us to do some calculations. It doesn't mean very much to have an inequality that we're trying to solve for. We just know it's greater than something. What we want to know is an equation we can actually use with an equal sign in it. So in that case, we do have to use reversible processes. Now, the entropy or disorder is going to be determined by the temperature. As you increase the temperature, you will always increase the randomness. Plus also, disorder depends on volume. You've got a finite number of molecules in a volume. The bigger that volume is, the more uncertain you are as to where the molecules are. So the entropy increases as the volume increases as well. Now, when both change, we can have an equation that delta S of the universe is greater than or equal to the log of a quantity, the heat capacity, times the log of the temperature final divided by temperature initial, plus R times the log of final volume divided by initial volume. So there's a temperature term, log of T2 over T1, and there's a volume term, log of V2 over V1. Temperature must be in kelvins. Volume can be in any unit because the units will cancel out in the ratio. Now, translational entropy. This is one of the ways molecules can have entropy. Um, it's, it's determined by the average translational kinetic energy, and that determines the temperature. I think I've told you before that the average kinetic energy of anything in any phase is 3/2 R. R has a value of 8.314 here. T, temperature in Kelvin. 3/2 RT is the average kinetic energy of any substance in any phase at whatever temperature you're calculating it. Now, molecules can move, translate in either the X, Y, or Z direction. So they can travel in any one of those three directions. There's actually 1/2 RT for each direction. That's why we get 3/2 RT, because we've got an X, Y, and a Z uncertainty. And each one of them is 1/2 RT times its temperature. The translation of a molecule causes uncertainty in location in space. And the translational entropy is large for everything at essentially every temperature that we're going to encounter in the lab. We'll see that will go to zero when we go down to absolute zero. It's not surprising the equation is 3/2 RT. Now, the other way that molecules can have entropy, atoms cannot, is rotational entropy. Now, an atom is considered to be a point spherical spot, and so it has no volume, and it has no particular axis to rotate around. So there is no rotational entropy for atoms, but if we talk about molecules, molecules can be rotated in space. And that's the next most important one. Now, if the molecule is nonlinear, then there are unique values for X, Y, and Z. So you can have rotational entropy around all three of those axes. But linear molecules have an axis, and we usually assign that as the Z-axis. And you can rotate the molecule itself around X or Y, but you can't rotate it around Z because remember, the atoms that make up that linear molecule are points that lie along the Z-axis. So there's no mass off the Z-axis, and there's no rotational entropy on the Z-axis. So there are three ways that nonlinear molecules can rotate, but only two ways that linear molecules can rotate. This gives rise to rotational uncertainty in the location of the atoms that make up a molecule relative to each other. So there is a rotational entropy. The most important one is translational. The next most important is rotational. And most every molecule are going to have some contributions of their entropy from these two sources. Vibrational entropy is the next most important, and I guess in the ones we'll look at, the least important, because molecules can vibrate relative to each other. So if you imagine a molecule vibrating, the atoms are moving back and forth, back and forth, back and forth. So there's some uncertainty into where each one of those atoms are located at any one time. Now, if you've got N atoms in a molecule, there are 3 coordinates for each one. So 3N is the number of total degrees of freedom that those atoms can have. Now, if we have nonlinear molecules, remember there are 3 ways that the molecules can rotate. So 3N minus 6 is the number of ways that a nonlinear molecule can rotate. There are only 3N minus 5 if we have a linear molecule. This motion now gives rise to vibrational uncertainty in the location of the atoms within a molecule relative to each other. Generally, the delta S, or the entropy of vibration, is small. It might contribute at higher temperatures. It contributes very little at room temperature. So when I'm thinking about the ways we can have entropy, the entropy of gases is mostly translational, and it's going to be very, very, very large. The entropy of liquids would be next. It will be bigger than the entropy of solids generally, but not much bigger. The primary component is going to be the gases. So when I'm looking at reactions that are taking place, I'll get a pretty good idea of how the entropy is changing if I just look at the gases and ignore the liquids and solids. Decreasing the temperature decreases the entropy and arrives at a more and more ordered state as you cool the system down. In the limit, a state may be reached that is perfectly ordered. That would be at absolute zero Kelvin. And this is another way that we use to define what absolute zero is. Absolute zero is the temperature at which you reach a perfectly ordered crystal. Remember, the other way we defined the absolute zero of temperature, was the temperature at which the volume of a gas goes to zero. And we argued that that is not a place that's likely to happen. So this law that you reach a perfectly ordered state at absolute zero of temperature is the third law of thermodynamics. Now, here's some problems. Let's take a look at them. And we're to calculate Q, W, delta H, delta E, and delta S when propane gas burns in oxygen at 1 atmosphere pressure. Now, our reaction is 1 C3H8 is propane, plus 5 O2s goes to 3 CO2 gases and 4 H2O liquid. Now, it is important to notice the liquid state. And in the PowerPoint, I've highlighted that with sort of a greenish color subscript so that we carefully consider the gases, especially when we're talking about entropy. Q is the heat flow at constant pressures. The problem said we were carrying this out at constant pressure, and that's equal to delta H. Now, we've learned we can calculate the delta H for a reaction by just getting the heats of formation of the products and subtracting off the heat of formation of the reactants. So delta H of the reaction, and that's going to be Q here as well, is going to be 3 times the delta H of formation of carbon dioxide, plus 4 times the delta H of formation of liquid water. Liquid water is important, minus the 1 times the delta H of formation of C3H8. Now, we can plug those values in. The delta H of formation of carbon dioxide is minus 393.5 kilojoules per mole, multiplied by the 3 moles that we have in the balanced equation. Plus, we're going to have delta H of formation of liquid water. There's a value for gaseous water, but we're not using it. The value for liquid water is minus 285.8 kilojoules per mole, and we're multiplying by the 4 moles shown in the balanced equation. And then we need to subtract off 1, the amount of propane shown in the balanced equation, times its heat of formation is minus 103.8 kilojoules. Now, if you do that math, you come out with minus 2219.9 kilojoules. Now, that's a very large number, and it's negative. Well, it ought to be. This is a fuel, and it does burn. and it produces a lot of heat. So the sign should be negative. We would always want to check that, and it is. And okay, now the work for ideal gases is going to be defined as P times the change in volume. So if we look at this equation, the volume is going to be determined by the number of moles in each case. And for this particular case, we have the number of product moles of gas is 3. Then the total number of reactant moles of gas is 6. Notice we left off the water, liquid. So we had minus for the formula, minus P delta V, times a minus 3 is going to give us plus 3, times the ideal gas constant is 8.314 joules per mole per Kelvin, times the temperature is 25 degrees given in the problem is 298 kelvins. This calculates plus 7.43 kilojoules is the amount of work that's done. And that means that work went into the system. Now let's check, does that make sense? Yes, it does. Because when we started out, we had a container that held 6 moles of gas in it. That's going to have a bigger volume than we get at the end when we have the container only contains 3 moles of gas. So the atmosphere, the outside, is going to push in and it's going to do work on the system when this reaction takes place. And that sign should be positive. Always check the sign. Be sure you're correct. Now, from the first law of thermodynamics, delta E is Q plus W, and we have the data we need now to calculate that. We calculated Q was minus 2219.9 kilojoules. We calculated the work was plus 7.433 kilojoules. And now if we do the math, we get minus 2212.5 kilojoules. Now, about all we can say here is I want to be sure that delta E and delta H have the same sign. They almost always do. In fact, I know of not one single example where that isn't true. Delta E and delta H almost always would have the same sign. And they're going to be roughly the same value. The only difference between the two really is the work done. So if you take delta H and you subtract the work off of it, then you come out with delta E. Okay, now to get the entropy, we're going to use table data in this problem as well. The entropy is the we're looking at the entropy of the products. So it's 3 times the entropy value for carbon dioxide as a gas, plus 4 times the entropy value for water as a liquid. And then we need to subtract off the 1 times the entropy of C3H8 and 5 times the entropy of oxygen diatomic and gaseous. Now, we can get those values out of the table. The entropy of carbon dioxide is 213.6 joules per mole per Kelvin times the 3 moles that we have. We add to that 4, the number in the balanced equation for water, and the entropy of liquid water is 60 plus 69.96 joules per mole per Kelvin. And we subtract off the entropy value of the C3H8, the C3H8, and we get minus 269.9. And subtracting also the 5 entropy moles of entropy for the water as a liquid is 205. No, I'm sorry, that was for oxygen, minus 5 times the 205.0 joules per mole per Kelvin for oxygen. If you do all that math, you come up with minus 374.3 joules per Kelvin. Now, if you look at this, does this number make sense? Well, It should be in that range of um, in joules per Kelvin, because that's what the entropy is. And um, the difference should be because of the entropy change that's taken place in the gases. So if you looked at um, the change in the number of moles of gas, it was -3. So the sign of the entropy should be the same sign as the change in the number of moles of gases, -374.3. That looks like a reasonable number. Okay. Now, a certain process is carried out at constant pressure. The heat flow measured by temperature change in the calorimeter is found to be -2200 kilojoules. In other experiments, the change in the internal energy is found to be -2190 kilojoules, and the change of entropy is -350 joules per Kelvin. So this is the data given. What is the value of delta H? Now this is a checkpoint problem. These are the ones you should work out on your own. The data up is given that you need in this problem. What is the value of the work? And assuming the heat flow to the surroundings is reversible and the temperature of the surroundings is 25 degrees, show that the delta S of the universe, which is the delta S of the system, plus the delta S of the surroundings, is greater than 0, because we know that process is spontaneous. Okay. All right. So that concludes the lesson on entropy. Um, If you have any kind of questions about it, I appreciate it if you would send me an email, or better yet, go to the discussion section on D2L and discuss them among yourselves, because the best way for you to learn something for yourself is to be able to explain it to someone else. All right, I'll see you at our next class meeting. Have a great day.